right, good morning. We're going to start today's class, and today's class we're going to continue with memory, but this time we're going to learn more about memory cache. So I will introduce the cache memory, then because the cache memory is very smaller than the main memory, we need also to learn some cache mapping techniques to allow the system to allocate some cache line to specific blocks from the main memory. But before that, get your English names ready and your PDX email for the attendance purpose. You have to scan the code using the WeChat, then enter the information. Please scan the code and enter the information, your English names and the PDX email for your attendance purpose. Done, right? Everybody has done with this, right? All right, so we're going to start today's class. As I said, we continue with a memory system, but this time we're going to learn about a cache memory. And here we have to review the typical relationship between a memory at level I and the memory at the next level in the memory hierarchy. So for each level we have a cost per byte, and we have also average access time, and we also have the average data transfer rate. We have also, for each level of the memory hierarchy, we have the total memory size. So we have this typical relationship between a memory MI, that is the memory at level I, and then the next memory at the level of I plus 1. So we have the cost for a memory at level I has to be greater than the cost per byte for a memory at the next level, that is I plus 1. When it comes to the average access time, the average access time for a memory at level I needs to be less than a memory at average access time for a memory at level I plus 1. For the average data transfer rate, we need the average data transfer rate for a memory at level I to be greater than the average data transfer rate for a memory at level I plus 1. When it comes to the size, we have the size for a memory at level I that has to be less than the size of the memory at level I plus 1. That means that a good memory has to balance relative size, cost, and the speed. So we need enough memory which can help us to store enough amount of data, but we need also to be fast to retrieve data with less time, and we need also to get it at an affordable price. So we need a memory which can balance these three factors: the speed, the size, as well as the cost. Now, we have this memory hierarchy. If you see this memory hierarchy on the screen, we have registers, then we have different levels of cache, and then we have the main memory, and then we have the secondary storage. So we see we have different levels of cache depending on the technology. We have level 1, level 2, level N. So here we see we have the memory cache, which is in between the central processing unit and the main memory. Why? Is because the cache memory is faster than the main memory, and it has to be there to avoid multiple accesses of the central processing unit to the main memory. This will help the system to improve its speed as the cache memory is there to store the most frequently accessed data. This will avoid the central processing unit to have multiple accesses to the main memory, which is slower if you compare it to the main memory, to the cache. So now we have the cache memory here, which is in between the central processing unit, to help the computer system to improve its performance by storing the most recently accessed data, which allow the cache memory to have more hits, and this will improve the overall computer system performance. Now, why the cache memory? The cache memory, it is designed to combine the memory access time of the most expensive and high-speed memory system, and also the large memory size of less expensive and the lower speed memory. Here, the picture on the screen, it depicts the single cache memory, which is in between the central processing unit and the main memory. And we see that the unit of transfer between the central processing unit and the cache memory is a weight. And we have a unit of transfer between the cache memory and the main memory, which is a block of the data. So we see that the link which is between the central processing unit and the cache memory has to be faster if you compare it with the one which is between the cache memory and the main memory. Now, the picture B is there to help us to understand that the cache memory may have different levels of cache. Now we have 3 levels cache organization. We have normally the level 2 cache, which has to be slower than level 1 cache, but it has to be largely bigger than level 1 cache. The same goes for level 3. It has to be slower than level 2 cache, but it is bigger if you compare it to the level 2 cache, and so on and so forth. So if someone asks you why the cache memory in the computer system, your answer will be it is there to combine the memory access time of expensive high-speed memory and the large memory size of less expensive. That means it has to be between the central processing unit and the main memory to avoid multiple accesses of the central processing unit to the main memory. All right, so we have the cache read operation. We have the CPU which receives the address, let's call it LA, from the central processing unit. Now, the system has to check if the block that contains the LA address is in the cache. If it is in the cache, that is a hit. That means the system needs to fetch the LI word, and it has to be delivered to the central processing unit, and it's done. But when the block is not in the cache memory, the fetch needs to be expanded, to be done into the main memory. That is the next level of the memory in our memory hierarchy. That means that the system needed to access the main memory for the block which contain the LA address. Now, it has to allocate a cache line for the main memory block. That means we have got the block from the main memory, but since we have seen that once that the block is found in the level I+1 memory, it has to be loaded into the level MI, as we see here depicted by this picture. So we need to have a cache line for the main memory block. Now, once we have got the cache line for the main memory block, we need to load the main memory block into the cache line. So we needed to load the main memory block to the next level, to the upper level in the memory hierarchy. Then we can deliver the LA when the CPU and the process is done. Make sure you do understand this cache read operation. So the CPU receives the LA address and has to check if the block is containing the LA address is in the cache. If it is in the cache, so it has to fetch the LA word and it has to deliver it to the central processing unit. If it's not, it has to get access to the main memory for the block containing LA address. Then needed to allocate a cache line for the main memory block. Once the system has allocated the cache line for the block from the main memory, it has to be loaded into the cache line, and the word containing the LA address will be delivered to the CPU, and the process is done. This is the cache read operation. Now we have cache memory and the main memory structure. We have the cache memory and the main memory structure. We have this picture on the screen which depicts the cache memory and the main memory structure. We have the cache memory which include different cache lines. We have lines from 0 up to C-1. These are the cache lines, line numbers. Then within a specific line, we have a tag. We're going to see what it is, a tag, and what is importance in the cache line. Then we have block. We have block in each cache line. We have blocks. Then we have different blocks, and we have the block length. This is the block length. We have the block length. Now, for this block length is a keyword. It is a keyword. This is a cache. Then we have, this is cache memory. Then we have our main memory, which is bigger than the cache memory. It does also include the blocks. Here we have the blocks. We have blocks. So here we have memory addresses. We have 1, 0, 1, 2, up to 2 to the power of n minus 1. And we have also word length. Here we have word length. We have the word length, and this is a block of data. This is a block of data. This is a block 0. And this block also has a length. It is a keyword. Now, you see that we have our cache memory, which is smaller than the main memory. That means that we cannot load all main memory blocks into the cache memory. So we need some techniques which can help us to load specific blocks from the main memory to the cache memory. So we have small size of the cache memory. Then we have to allocate a main memory block to be in a specific cache line. So we're gonna define the following terminology, which can help us to understand the length of the cache memory structure. We have a block. A block here, you can see it is the minimum unit of transfer between the main memory and the cache memory. This is the block we are talking about. You see here, we have a block that is a unit of transfer between the cache memory and the main memory. Then the next we have a plane, which is a term that we do use sometimes to indicate the physical location of a block into the cache. What is the physical location of the cache? That is a plane. Then we have a line. A line is a section of a cache that holds one block. You see, this is a line of cache that holds what we call one block, and it is typically represented by a horizontal line. It does also include control information. We're going to learn about this. Then the next part of the cache is a tag. We have a tag here in this picture, the tag which is a part of the cache line, and it is there for addressing purpose. So we needed to understand the block, which is the minimum transfer between the cache memory and the main memory. Then we needed the frame which is there to indicate the physical location of a block in the cache. Then we have the line. Here the line is a section of the cache which contains one block, and it is typically represented by a one line. Then we have a tag which is a part of the cache line, and it is there to help with the addressing. Now we have element of the cache design. We have two different features. One is logical cache, and the other one is physical cache. So in the first feature, we have the cache memory, which is in between the processor and the memory management unit, and we have the cache here in the second feature, which is the physical cache. It is placed between the memory management unit and the main memory. That means that in the first feature, feature A, the system can fetch data from the cache memory without the interaction of the memory management unit by using the virtual address, the local address. So this way is faster because the system does not need to do any address translation. We now have logical addresses which can be used to get access to the data into the cache memory, and it does not include, it does not require the interaction of the memory management unit. So we have cache memory here placed between the processor and the memory management unit, MMU. That means we have a virtual cache, we have logical cache. That means we needed to use logical address to fetch data from the cache memory. That means the system can fetch data from the cache memory without the intervention of the memory management unit. This way is fast. So for B, we have physical address, logical address, and for B we have physical cache. This way need the translation from the logical address to the physical address, which is done by the memory management unit. That means that since the cache is placed between the memory management unit and the main memory, they need to do the translation of the logical address into the physical address to retrieve data from the cache memory. This way is slower if you compare to the logical cache. Now, how about the cache size? What is the minimum cache size, or what is the maximum cache size? This is something that needs to be discussed because the cache size should be smaller enough to keep the average cost per bit similar to the main memory. So we need to keep the average cost per bit for the cache memory to be small, to be similar, to be equals to the average cost per bit of the main memory. That means the size of the cache memory needs to be smaller as possible. But the cache size also needs to be larger to make sure that access time is closer to the cache of the cache alone. We have then cache memory which is bigger and they require more gates for addressing. So that's why we need to balance the size of the cache memory as well as the cost of the cache memory. Because if you try to make them much bigger, that will require more gates, and this will make slightly them slower than smaller ones. All right, we have some examples of cache sizes of some processors. We have the mainframe, that is IBM 360. We have this cache size, which is between 116 and 32 GB. And we have the mini computer, which is 150. And we have seen that with advancement of the technology now, there are more than one level of the cache memory. You see, we have which include the two levels of the cache memory, and the size is between 2 to 512 GB for the second level of the memory. And we have the first level of the memory, which is 8 GB for instruction level 1 cache, and for data instruction for data level 1 cache. Now, when it comes, for example, Intercall, which was introduced in 2017, that is a workstation, is a server. We have this much of level 1 cache, and we have instruction level 1 cache and data level 1 cache. Then we have also level 2 cache. We have as well level 3 cache. So there are much improvement when it comes to the size of the cache memory. Now, we need to talk about the basic of a cache regarding references. Now, let's imagine we have this cache content. This is the cache content. We have x4, x1, xn minus 2. But you see, this time, the cache does not include the xn data, does not include the xn block here. So this is before the reference to xn. Now, imagine the system is fetching the xn block from the cache and the block is not there. So before the request, xn is not there. So this is the content of the cache before the request of the xn. So requesting xn from the cache memory is a miss. That means the block is not in the cache memory. The block does not belong to the cache memory yet. Now, the system needed to fetch the block xn from the next level of the memory, that is the main memory, and it has to be inserted into the cache memory. So this is after the reference of the reference to xn block. That means the system needed to find a cache line for this block. So we needed to talk about why the system decided to put this block at this place, not at this one, because we do have two different empty lines in the cache line before the reference to the XN block of data. So we needed to discuss why does the system decide to include this block at this cache line, not at this one. This is something that we do discuss later on in this class. So before the request of this block of the data, the XN was not present. So that is a miss. A block of data is not in the upper level, it is a miss. That means the system needed to fetch the block of the data in the next level of the memory. That is the main memory in our case. Then once the system has found that the block is the block memory, it needed to allocate a cache line for the block, and the block needed to be loaded into the cache memory. Now, when there is a miss, when the data is not found in the upper level of the memory, that is a miss. We have three different types of miss. The first one is the compulsory miss. Now we have this block, this cache line. Let's say we have 8 cache lines. 1, 2, 3, 4, 5, 6, 7, 8. So we have a cache line. We have this cache memory, and it has 8 lines, 0 up to 7. Now, compulsory miss. This is the first time to the word. That means the word has not been never loaded into the cache memory. That means that here we have the cache memory, which is that means this is a cache compulsory miss, because the word that the system is looking for has never been loaded into the cache memory. That is a compulsory miss. So what can you do with the compulsory miss? There is nothing we can do with the compulsory miss, because if the word has never been loaded into the cache memory, as a result, this will result in what we call compulsory miss. Now, the next type of cache miss is capacity miss. Now, imagine we have this cache x0, which includes the following block: x1, x2, x3, x4, x5, x6, and x7. Capacity miss. That means we have a cache which is too small to hold all needed data. That means all the blocks need to be evicted to found a new cache line for a new block from the main memory. Now, here, let's say we have this cache with this content. Now, if we have one more block from the main memory, let's imagine x8, and you see there is no any cache line left. That means this block needs to be, one of these blocks needs to be evicted to found a new cache line for this new block from the main memory. So that means we need, for example, to evict x6, and we put x8. Now, in the future, when the system needed to reference again to the x6 that was evicted, that means it is a capacity miss, because the system has evicted the block to get a new cache line for the new block from the main memory. Now, the third type of cache miss is conflict miss. We also call it co-region miss. That means we have multiple words that compete for the same cache line, for the same cache spot, especially in the direct mapped cache. That means that we have two or more blocks from the cache main memory that needed to be loaded into the same cache line. So that's what we call conflict miss. Two or more blocks from the cache memory, they are competing for the same cache line, for the same cache spot. So we have these three types of cache misses. We have compulsory miss. That means this is the first time of access to a word, and it has never been loaded into the cache line. So this is a compulsory miss. There is nothing you can do with this type of miss. You need to have this type of miss. The next one is the cache memory, the capacity miss. That means we have a too small cache memory size that cannot hold all the needed data, all the needed weight from the main memory. So this is a capacity miss. We're going to discuss some techniques that we can use to minimize this type of misses. For conflict miss, or we call it also collision miss, that means we have multiple words from the main memory that need to be loaded into the same cache line. So they are computing for a same cache line, especially in what we call direct map caching technique. So we're gonna discuss about the different techniques that we can use to minimize the capacity miss as well as the conflict miss. But for the compulsory miss, there is nothing we can do it because this is the first time access to a word which has never been loaded into the cache memory. Now, how does the system found a cache line for a specific block from the main memory? It has to use different cache memory mappings. So a cache memory mapping is a technique that is define how blocks from the main memory are loaded into the cache memory. So the goal is to balance the speed, simplicity, as well as the flexibility of the memory system. We have three different cache mapping techniques. The first one is direct map. The second one is fully associative. The third one is set associative. Now, let's get started with the direct map. For direct map, we have a word from the memory, main memory, that needs to be assigned to a specific cache line. So we have each memory location which needs to be mapped to a one cache location, a one cache line. It uses the following mapping method. We have the cache block, that is equals to the block address mod the number of the cache line or number of cache blocks. For example, if we have 8 cache lines, the block number 12 from the main memory will be loaded into the cache line number 4 because we have to do 12 modulo 8. Now we have direct maps. We have cache line or cache block equals to block address mod number of cache blocks. Number of cache lines. Now, imagine we have 8 cache lines. 8 cache lines. And we have block number 12 from the main memory, block 12 from the main memory. Then to find the cache line for this block, we need 12 mod 8. 12 mod 8, then we have 4. So that means our block number 12 from the cache memory will be loaded into the cache line 4. So we have the cache here. We have a cache here that includes 8 lines. 1, 2, 3, 4, 5, 6, 7, 8, 0, 1, 2, 3, 4, 5, 6, 7. Line number. Now, this is the direct mapped cache mapping. We have a block 12. Block 12 from the main memory that needs to be loaded into cache line 4. Because we do 12 mod 8, that is 4. That means we have this block 12 loaded here. The block number 12 will be loaded here. And this is a miss. Hello? Are you there? Now, based on these cache mapping techniques, we see that the block number 1 from the main memory will be loaded into the cache line number 1 because we do 1 mod 8, that is 1. So the block number 2 will be loaded in which cache line? In which cache line? 5 number 2. The block number 2 will be loaded in which cache line? We have this example. Block 12 from the main memory will be loaded into the cache line number 4 because we do 12 mod 8 since we have 8 cache lines. Now, the same here, we have 8 cache lines. We are trying to find in which cache line each block from the main memory will be loaded. Now, we have the block number 1 here, which needs to be loaded into the cache line number 1 because we do 1 mod 8 equals to 1. 1 mod 8 is 1. So this means that the block number 1 from the main memory will be loaded into the cache line number 1. Now, block number 4 will be loaded into which cache line? 5 number 4. 5 number 4. Which cache line? We have to use the same technique. We do 4 mod 8 is 4 mod 8 is modulation is the remainder of the division. You divide 4 by 8, then what is the remainder? 4 divided by 8 is, what is the remainder? 4. So the block number 4 from the main memory will be loaded into cache line 4. How about block number 8? Block number 8 from the main memory will be loaded in which cache line? We have 8 cache lines, and we are using the direct map caching. Number 8. Number 8, class 5, number 8. In which cache line? You do? 8 mod 8 is? 8 mod 8. Huh? 8 mod 8 is modulo. Is this the first time you hear the modulo operation? Hello, everybody. Mod means what? For modulo operation, if I do 12 mod 8 equals to what? Is 4. We do 12 divided by 8, right? 1, then 8, 12 minus 8 is 4. So the answer is this one. The modulo is the remainder of the division. Okay? Clear. Then block number 8 will be loaded in which cache line? Block number 8 from the main memory will be loaded in which cache line? We have 8 cache lines, and we are using the direct map caching technique. 8 mod 8 is? 8 mod 8 is? 5 number 1. Is 0, because 8 divided by 8, the remainder is 0. That means the block number 8 from the main memory will be loaded into the cache line 0. Then we have the block 8 here in the cache line. Make sure you do understand this. Now, to check if a request word is in the cache, the system needs to use the tag. We have seen that the tag for the cache line is there for addressing purpose. Then a tag needs to store a part of the memory addresses, which is there to indicate that the data is in the cache line or not. So only the upper part, the upper order of the bits needed to be the addresses for the tag purpose. So we need only the upper, that is the high order bit of the address that are stored in the tag to indicate if the data is in the cache or not. So the lower bits are used in the index to select a cache line. For example, if we have a 5-bit address and 8 cache lines, we need 3 bits, the lower bits, that are there to indicate the index, that is to select the line in the cache. Then the upper 2 bits, they are there to be used for tag to verify if the data is correct or not. So a hit happens when the tag in the select line matches the requested address. So the hit is happening when the tag in the selected line has to match the requested address. Now we have the direct map. Here we have different address of the reference. We have the binary representation of each reference, and then we have the hit or a miss in the cache. So this is something that we're gonna do together. This is a 5-minute break. Take your break. We're gonna resume class after break time.